In the remainder of this course, we shall use the logic that has been treated extensively in the preceding lectures to precisely define and discuss other mathematical topics. And we start now with the notion of set. Everybody probably has an idea of what is a set. Perhaps the first thing you think of is the scoring system in tennis, where a set is a bunch of games. Or perhaps you think of a cookware set, a bunch of tools that allows you to cook. Intuitively, a set is a collection of things of the same type. So, for instance, a box of chocolates can be considered to be a set. And here you see a picture of a stamp collection, or perhaps of a set of stamp collections. You have probably also already encountered the notion of a set in a mathematical context. Let us consider some examples. If the natural numbers 0, 1, 2 and 3 are grouped together, then they form a set of numbers. We use curly brackets to actually form the set. The notation is important and has a meaning. It makes explicit that we intend to group the numbers. But also, it tells us that we do not care about the order in which the numbers are listed, nor about their multiplicity. So, the set containing the numbers 0, 1, 2 and 3 is equal to the set containing the numbers 3, 1, 0 and 2. And it's not important whether we list the numbers appearing in the set more than once. The only thing that matters is whether the number occurs in the set or not. Sets are allowed to be infinite. I'm sure you are familiar with the following symbols denoting certain infinite sets of numbers. The symbol n is often used to denote the set of all natural numbers. Please note that in this course we adopt the convention that 0 is a natural number too. Similarly, we have the symbols z and r denoting the sets of integers and real numbers, respectively. We introduce a binary predicate denoted by the Greek letter epsilon to express that something t is an element of the set x. Now, if we take concrete values for t and x, then we get a proposition. For instance, we get a true proposition by taking 1 for t and the set consisting of the numbers 0, 1, 2 and 3 for x. We pronounce the obtained proposition as 1 is an element of the set consisting of the numbers 0, 1, 2 and 3. We get a false proposition by taking 4 for t instead. 4 is not an element of the set consisting of the numbers 0, 1, 2 and 3. That something is not an element of some set is often denoted with a crossed out epsilon. Listing the elements of a set between curly brackets works fine for small sets, but for large or infinite sets it's very impractical. So we now introduce a more sophisticated method to specify the elements of a set. Suppose we have a set X and a predicate that expresses a property of the elements of X. A property that elements of X may have or may not have. Then we use the following notation to specify the set of all elements of set X that satisfies the predicate P. Thus, we can now specify the set of natural numbers greater than 10. And the set of integers x satisfying x squared plus x is less or equal 0. The intuitive interpretation of the set specification mechanism is made precise with the following property of the element of predicate. Consider the predicate t is an element of the set of all elements in x satisfying the predicate p. The property of element of states that this predicate is logically equivalent to the predicate t is an element of x and t satisfies p. This property of element of, formulated here, should not be regarded as a property that can be proved. It should be regarded as an axiom of set theory. It defines the interplay between the element of predicate and the set specification mechanism. We shall use this and other properties later to prove statements about sets. We now have a mechanism to specify complicated sets using predicates. But you may have already observed that in order to use the mechanism, we should have a set X that contains at least all those elements that we would like to put in the new set. So it would be nice to have some kind of absolute universe that contains everything that we would ever like to put in any set. However, as Russell's paradox shows, such a universe, such an absolute universe, cannot exist. It's logically impossible. Russell's paradox is outside the scope of this course. But on the internet you'll easily find good explanations of the paradox. For the purpose of this course, it is still convenient to refer to a relative universe. The symbol U will denote, in a certain context, the set of all relevant things, numbers, sets, etc. The symbol U is characterized by the property that states that everything T is an element of the universe. Again, let me emphasize that the universe is relative to the context. It is a convenient logical tool, but does not have an absolute mathematical interpretation. We proceed to define and discuss another important predicate pertaining to sets, set theoretic equality. We say that two sets are equal if they have exactly the same elements. So for instance, the set containing the numbers 0, 1, 2 and 3 is equal to the set containing the numbers 3, 1, 0 and 2. Remember, the order of the elements does not matter for a set. Also, the set of all integers greater than 0 is equal to the set of all natural numbers not equal to 0. And the set of all integers satisfying the predicate x squared plus x is less or equals 0 consists of the numbers minus 1 and 0, because minus 1 and 0 are the only integers that satisfy the predicate. We define the equality predicate on sets A and B with a formula that expresses that A and B have the same elements. The predicate A is equal to B is logically equivalent to the formula stating that every element of the relative universe is an element of A if and only if it is an element of B. Note how the formula defines the equality predicate on sets in terms of the more primitive element of predicate. You may also note that the domain of the universal quantification is true by the property of relative universe. For this reason, the domain specification stating that X is an element of the relative universe is often omitted from the universal quantification. We introduce a symbol to denote the unique set without elements, the empty set. The empty set can be defined as follows. It is the set of all elements in the universe satisfying the predicate false. Let's formulate some standard properties involving the notion of empty set. The predicate T is an element of the empty set is logically equivalent to false. The predicate A is equal to the empty set is logically equivalent to the formula for all x in A false. Both properties can be derived from the definitions of empty set and equality on sets using the property of element of and standard logical reasoning. The mathematical theory of sets does not start with a precise definition of what is a set, as you might have expected. This has to do with Russell's paradox, which states, or which has as a consequence, that there is no absolute universe of all sets. Instead, we have introduced symbols denoting special sets, and we have introduced two binary predicates on sets, and we have introduced a mechanism to specify sets using predicates. We have, for instance, used this latter mechanism to define the empty set. This concludes our introductory lecture on sets. In the next lecture, we will discuss operations on sets.